Today, we actually have a very special speaker, Professor Ashutosh Dhekne, correct? Yeah. He's assistant professor in the School of Computer Science at Georgia Tech. He came to Georgia Tech in 2019 after receiving his PhD from the University of Illinois at Urbana-Champaign. He also holds a master's degree from the Indian Institute of Technology in Bombay and a BS in Computer Science and Engineering from Pune University. In 2022, he was awarded an NSF Career Grant, and in 2023, he was named a BBISS Faculty Fellow. His research interests are in mobile computing, Internet of Things, and wireless networking. And today he's going to be talking about UWB, ultra-wideband, right? And data reduction strategies for a greener planet. So,
thank you so much. Thank you so much for the introduction. So hello everyone. As you said, my title for today's talk is Through a UWB Looking Glass, which is data reduction strategies for a greener planet. For those of you who have not looked at Alice in Wonderland, this is actually a very interesting phrase from Through the Looking Glass is actually the title in a comic little children's book. But what I'm trying to say here is, instead of trying to look through the lens of cameras or through the lens of our usual vision processing systems, we are going to change our lenses and go and look at the world from a slightly different angle, and UWB I will define, of course. So computing industry, right? And I'm going to begin this bunch of slides, which are actually boring because I came up with the slides recently, is an interesting piece in the entire carbon footprint world. Okay. First, it's extremely difficult to calculate. Why? Because if you had a car and you were running a car a certain number of miles, you actually need a certain amount of actual fuel to be put into the car. And so it's actually easy to say, here is my fuel, and therefore I burned that much fuel, it will emit this amount of carbon dioxide. Similar for many, many other industries. So you produce energy from burning coal, you know exactly how many kgs of coal you burned, how many kilowatt hours of energy you produced, so you know what your carbon footprint is. But from a computing perspective, there are operational costs, there are embodied carbon costs, there are individual usages like our computers, and there are usages that are happening at the data centers which we don't actually see, right? And therefore, by some estimates, computing just at the data center is somewhere between 1 to 2% of global emissions. Okay, and this is almost equivalent to the airline industry today. 2% is 2.4% is the airline industry, and these estimates have been fluctuating. Okay, but I took the lower and the slightly middle ground here. So 1 to 2% is the global emissions just from data centers, and it's estimated to increase to about 5% in the next 20 to 30 years based on how we do the decarbonization. And I will talk about that relationship in a little bit. But if you think, or if you look at this global picture of the greenhouse gas emissions by sector, computing doesn't even show up. There's transport, there is energy consumption in buildings, there is energy usage in industry, there's agriculture and forestry and land use and change of land use, even waste, landfills and wastewater. But computing just doesn't show up because it's not big enough, right? Which might lead to everybody saying, hey, so why should we care, right? Essentially, this lecture is completely meaningless because no matter what we do, we can't really benefit anything. Right? But here's the reason why we should all care. Because computing done right can decrease the energy usage in every other sector that you saw. Okay, so there is an interesting opportunity. While computing itself maybe does not even appear in the chart, it can actually do a lot or influence that chart quite a bit. And how computing just completely reduces the need to travel. Right? And we have seen that through telecommute and so on. Using video conferencing, we require less daily commute. We can actually have experiences that are brought closer to us rather than we having to visit everywhere through AR, VR systems, or just through our modest living room TV, right? We can have movies at home. You can be educated at home. You could work from home. You can play at home. You can even enjoy festive events at home. So this has become my pet favorite, which is on 31st night, we spend that evening or that night at home just watching a YouTube channel for different countries as they celebrate their own New Year's, 31st December, right? Perfect, because I don't have to go anywhere and I see in high resolution, right, without having to travel or any of these problems, fireworks in every city as it happens. Computing also reduces the need for paper, and paper industry, by the way, is actually a large contributor. So no physical bills that come in the mail, less paper mail in general, but computing also improves efficiency by allowing us to monitor temperatures in our house, energy consumption at large buildings, small buildings, and everything in between. And it also allows us to monitor supply chains. But I'll give you another nice example, which I did not put in the slides, of how it improves efficiency. It is due to the existing of computing industry and GPS in particular that we can actually travel much faster on our highways now than we could previously, because we are guided much better by GPS than by the boards on top of the road, which means every vehicle that is making these trips is actually running more efficiently now. By the way, there are ways to actually take this location information as input and improve efficiency as well. Also guiding people from different pathways, and that's something that Google Maps has incorporated, also improves efficiency. So Google Maps has now started to give us options. This is the fastest road, but really this is the one that is more fuel efficient. Right? And all of that only happened because we now have a much better understanding of maps, where people are and where they are commuting to. Right? So you have a general global picture, which would have not been possible if even we were trying to solve this without the computing aspect, just by talking with satellites individually. And then computing allows for a certain amount of decentralization and democratization, which improves access to information and resources for everyone. Right? And there is this concept that is building up, which says, if you want to do any decarbonization of any of these industries, you want to think about a digital equivalent, right? And that's how you can get the same outcome or the same progress without actually having to spend carbon on it, right? And think of it this way, right? For any progress to make, humans have in the last 150 years spent carbon on it. But now maybe we can spend this digital currency, which is like computing, which doesn't use that much carbon, to actually make progress. But there are pitfalls in this journey, and that's why this talk. We are generating too much data. Okay. And a large fraction of that data is essentially being thrown away. So we are not really using it. We're just generating a lot of data, which means we are spending energy on collection of data. We are spending energy in transmission, and we are spending energy in processing of data. There are also privacy concerns. So you're collecting data on a street. There are privacy concerns about people's faces being recognized and so on. And video data could easily leak too much information. But the problem is not just video data. Even too much geolocation data could also invade privacy, right? For example, Google Maps now gives me a general trajectory of where I go. It knows where I work, right? All of that. Right? It is a certain amount of invasion of privacy, whereas I actually gave it the permission to do so. Eventually, I will have forgotten that I actually gave it that permission. Right? And just yesterday or day before, I got a report from Google saying you have visited a total of 123 cities. Like, wow, that's great in the last 2 years or so. That's great. The cities are just Marietta, Atlanta cities. Okay. 123, I'm proud. So if my wife says you don't go anywhere, I'm going to show her that. 123 cities. What do you expect? too much geo information. Okay. And larger machine learning models are required to process any of this huge amounts of data that we collect. Okay. So we have this double whammies. We are spending more energy in collecting all the data. Most of it we need to throw away, but to process it, we have to also spend so much energy in all the machine learning tasks. And AI is particularly energy intensive, primarily because you give it a few GBs of data and the answer comes out, this is a face of a dog or a muffin. Right? Literally, this information is encoded in like 5 bytes or 10 bytes of information, whereas we gave a billion times as much to get that data out. Okay, of course, training is slightly different than testing, which means when you ask a question, what is this? Is this a muffin or a face of a dog? That takes much less energy. It's the training that takes most of the energy. Okay. And that's why this talk, which is trying to talk about tiny data, rather than collecting this huge amount of data and then throwing it away, try to find concentrated ways in which information about exactly what we need to study can be extracted. Right? It reduces privacy issues because you're not getting face information. You're not seeing the face of anybody. You're just seeing that there was some individual tagged by some number or ID who went from here to there. Right? It also reduces energy costs for capture because you're capturing a few bytes. Storage, you're again storing a few bytes. Transport, sending only a few bytes across the internet. And interpretation of data because there is really only that much data to start with. How big can a machine learning model be? It allows a democratizable, decentralized, and disconnected economy to thrive. Democratizable because anybody can produce a little bit of data, right? But only a few people could actually produce and transmit bulk of data, huge amounts of data, because it takes money to actually send that data across the internet. Decentralized because decisions could be made by smaller computers like our mobile phones or our laptops instead of being centralized in a cloud computing facility. I'm happy to take questions at any time. Okay, so feel free to.
So, okay, you invited. Okay. So this is the, as a paradigm, this is the exact opposite of like a pre-trained transformer type of approach, right? Where you dump like a ton of data and have a trained super heavy model.
It is not opposite of that, but instead of dumping a huge amount of data to learn some attributes, you actually learn, you know that you want a certain thing, and we'll talk about lots of these opportunities, okay? But suppose you know that you want to look at human action, okay, there's movement, gestures. Okay? Instead of taking the entire video feed of how this person is moving, if we were to just say this hand and this hand had a distance of 20 centimeters, 1 meter between each other, the amount of data we used to encode that is much lesser. And now, yes, you do train a classifier on that, but you started off with a much smaller number, right? And also allows you to do a disconnected amount of, because you don't really need to rely on cloud when you have small amount of models. Models are small, data is small. You can also do disconnected processing. And my talk today, I'm going to talk about a bunch of things, okay? But don't be overwhelmed because we'll go nice and slow and only talk about things that are really important for this topic, okay? But we will talk about physical distancing in COVID, right? Jump to access to educational material, okay, by streaming the pen's location. Talk about wearable technology for doing that gesture. Then talk about physical intrusion in houses and so on, pet tracking and interactive art, and all of that without using cameras, right? And that's precisely the crux of this talk. And let's begin with 6 feet apart, which is the project that we did almost immediately after coming to Georgia Tech, 6 months later, because COVID started. Before we do that, I want to introduce a new sensor. We are all familiar with cameras and what cameras do and how they capture images and so on. But there is a slightly different way of thinking about the world as well, which is from radio frequencies or from radio transmissions. And ultra-wideband radios are one such thing. And you might know of the technology because it exists in the air tags, notorious these days for tracking spouses and so on, but also for other good reasons, like tracking your lost baggage on airlines. Okay, but it's also present in the latest iPhones, the latest Samsung Galaxy phones, and Samsung has also come up with its own smart tags and so on. Support for this technology is being developed by the FIRA consortium and the UWB Alliance together, right? But literally the companies here are all of the companies that exist in the IoT space, and right from the chip manufacturers like NXP and Qorvo, all the way to application developers like Google and Apple. And Bosch is interesting because Bosch is looking at UWB from connected car perspective, because they create the car components. They're also looking at appliances and so on. Okay, so it's actually a huge new ecosystem that's coming up, and it's silently creeping on us without actually, becoming a hype yet. Eventually it will. But what is ultra-wideband? Very similar to Wi-Fi, it's basically a wireless technology to do data transfer. Okay, the big difference being instead of using narrow frequency bands, like for example, Wi-Fi uses 20 to 40 megahertz worth of bandwidth at 2.4 gigahertz center frequency, UWB, as its name suggests, uses a larger bandwidth, about 500 to 1 gigahertz bandwidth. So it might be at frequencies starting from 3.1 gigahertz, anywhere to about 10.6 gigahertz. But any signal that is sent already occupies a very, very large band. Whenever you have signals like these, it will overlap on Wi-Fi and you wouldn't be able to communicate over Wi-Fi. It will overlap on Bluetooth, you wouldn't be able to communicate over Bluetooth, GPS, somewhat similar, right? But you'll have a lot of problems. And therefore, FCC limits the power at which you can transmit the UWB signal. Okay. However, think of when you have a large bandwidth, what do you gain? You can now construct a signal which lasts for a very, very small amount of time. Okay, when you have a lower bandwidth, the signal has to last for longer time. When you have a higher bandwidth, the signal could last for a much shorter time, which also means that you can send many of these one after another, and you can encode it in a manner such that any other interruptions or any other interferences can cancel out. Okay, and because it's a short time for which you're sending a pulse, now you can start to measure the amount of time it takes for these signals to go from a transmitter to a receiver very, very precisely. Right? We are talking about nanoseconds level of precision, which means light is, or the electromagnetic waves are traveling for about 1 feet and you can detect them. Right? Speed of light is 3 into 10⁸ meters per second. So you are essentially talking about going around the Earth in 0.1 seconds. Right? And we are able to detect that wave at 1 feet distances. Okay, so it takes good amount of technology to be able to do that. But also, because of the FCC standards, very low power, very high bandwidth, allowing us extremely low data rates. Right? Everybody likes high data rates, right? But UWB is actually a technology that allows you low data rates, 110 kbps to 6.8 mbps. That's the max. That's even lower than the minimum that Wi-Fi supports now. Okay. But allows an indoor range of about 50 to 70 meters, comparable to that of Wi-Fi. And its real power comes from that short pulse that it can send, so that you can measure distance as well. Now, we knew how to do that, right? We knew how to do distance measurements, and along came COVID. And one of the most important things in COVID was to try and make sure that people don't come within a certain distance of each other. Okay, and most approaches at that time were not asking this first question. The first question is, am I at a safe distance from others? That's really the right question to ask for keeping yourself safe. But rather, most of computing industry, or mobile computing industry, was asking this next question, which is, did I come in contact with someone who is already infected? Okay? And it might seem like these are duals of each other. Okay, it might seem like if you know the answer to one, you also know the answer to the other. But from a data perspective, it makes a massive difference. Right? So if you ask this question, did I come in contact with somebody who is infected? You're talking about, for all of the previous 15 days, keep data about everyone I came in contact with and know who amongst those have been now diagnosed with COVID. If you ask this question, am I at a safe distance from others? It's here and now. I don't know any other person in the grocery store, but I'm only asking a simple question, am I at a safe distance from all of them or not? Which means for contact tracing, it's creating a null set. There's nobody in the contact tracing app at all, right? And that's the approach that we took, where we said, well, we'll develop something very simple. We can embed a physical distancing function into a wearable device. And maybe that wearable device can be carried by doctors, by nurses, or just embedded into the shopping carts. Okay, and we know if these two shopping carts come too close, we'll start to beep and make sure that people separate out and remain at a safe distance. This would be relatively low cost. It's still not, the cost exists, but it's relatively low cost because we want to develop something that is infrastructure free without requiring entire establishments to deploy sensors on their walls. Okay. We want it to be reconfiguration free, where it would work even when only a subset of the devices are together. Think about shopping carts, right? There are a bunch of shopping carts, but only the ones who are in one aisle really matter at any given time. Right? And we wanted to enable a lightweight solution which would go across grocery stores, hospitals, factories, and warehouses. There are three main problems. One is hardware. What is the hardware that we would have, which would beep after this distancing and so on. Second is how do you design a one-to-many ranging protocol to allow distance measurements between many such cards? And how do you perform accurately despite some obstructions, people walking, aisles being present, etc.? It becomes a difficult problem. Right? So occlusion detection is basically saying there's another person behind a wall. I shouldn't care about it, right? Because, well, the distance doesn't matter. There is a physical barrier, and therefore viruses cannot be transmitted from here to there. We are fine. And warning should be disabled. But on the other hand, if there is another person walking through, that's actually an even worse scenario, as like too many people within 6 feet. And you should remain, the device should alarm you, even if there is somebody walking between you. And these, technically speaking, are slightly different questions, because from a wireless reflection perspective, you get different reflection patterns, right? And here are those two different reflection patterns. You typically get a line of sight pattern, which is this dotted line, which is very clean, which tells you exactly that there is nothing in between these two devices, and then you can measure distances properly. But a lot of times you get an attenuation because something like a physical wall blocking it. It's a lowered signal, the lower strength. Or if a human is walking along, the first path gets blocked because human body has a lot of water. And then there are lots of other tiny paths that add up, and this creates a mess of a channel impulse response. And you can still detect that maybe this looks like a person walking through rather than being an obstruction or a wall. Once again, we are talking about, so this is like 1 KB of data per instance, and we're talking about some 10 such instances per second, which is all locally resolved and thrown out. The only purpose of this data is to make sure that if two people come, this is the evaluation setup, but if two people come too close, I'll show you this. There's a buzzer over here which starts beeping, right? That's it. I don't know who that other person was. I don't know what their ID was. I just don't want another person to come within 6 feet of me, right? Even beyond the pandemic, when somebody is experiencing flu-like symptoms in a grocery store, they could just enable a button. Actually, we had a button on the backside of this. Just enable a button saying, I don't want to warn generally, but today I am feeling sick. It would be useful for the community to not really come too close. Okay. Solutions like these. So solutions like contact tracing, for them to work, everybody has to adopt it. But solutions like these can be adopted by just one grocery store in a place where rather elderly population lives, and you immediately start to see the benefits, because that's the one point where a lot of contact would have happened. Right? So very localized solutions can be created by rethinking the problem in some way. Okay, what are the type of data reduction aspects? Simple machine learning module. All that is doing is looking at this channel impulse response, really 1 KB data. It runs on the device without internet connectivity. There is literally no chip to connect to the internet at all on this device. In many settings, there is no need to keep IDs of a person, so the contact tracing happens. In some settings, it's actually useful. For example, to create a bubble between doctors, it's actually essential to have those IDs. But that's a very small setting. It's not talking about the entire population and you went on a bus somewhere, right? So that's a small amount of data that needs to be kept. And in operations, there's no data that is produced as an output of this system. It just beeps and hopefully make sure that people are away from each other. And if this works, the amount of data generated by contact tracing apps is also reduced, right? Because you just didn't allow too many people to come into contact with each other in the first place. Incidentally, after we worked on this, and because there were teams in other universities who were working on contact tracing, at the time when I adopted these slides to actually teach into my course, I did actually check with the contact tracing team in the University of Washington to make sure they would be okay me publicly saying this differences. And it was very nice to actually see how much on the same page everyone was. So sometimes it's useful to have, these kind of interactions. Of course, those teams are much larger. Google, Apple, Microsoft, University of Washington, all coming together to create the contact tracing. I was a little player at that time, working almost alone. Okay, questions, thoughts?
Why not keep the data? If I know the time and location of when I was within contact, wouldn't that be useful?
Yeah, so it is assuming that you are using a, okay, in some scenarios, it makes perfect sense. The doctors and nurses is a good example, for example, in these possibilities of how you use it. But on a cart, on a shopping cart, right? Anybody picks any shopping cart and starts to move around in the grocery store. And having to enter some sort of ID into that machine is not always desirable. Right? So that's why there is a barrier to having those IDs in the first place. But indeed, if you do have the IDs and it's going to be useful for contact tracing, the system allows you to do that. There's nothing from a system's perspective that disallows keeping IDs. Right? And precisely for that reason, we did have this SD card over here, which actually could save a lot of data if we wanted to. But it was not an online system. That would need hardware modification.
But isn't the potential for utility of the data the reason why people keep data that they don't necessarily need? Because there's
always true. There's always a potential
for some future use.
Correct. In this particular application, though, contact tracing was so riddled by privacy concerns that even contact tracing data itself can no longer be used for scientific studies, simply because there is not enough data that gives us any useful information, because those IDs were reset after time and you have no longitudinal studies done, etc. So even contact tracing, which was actually generating and keeping all of this data, was still short-lived, and even that didn't yield really good insights.
So Ashutosh, just a clarification. So this is fascinating, but somewhere in this story, I missed, I lost the UWB piece.
Okay.
So how are you using the UWB aspect in this, and could this not have been done if UWB did not exist? So can you clarify that?
Sure. So the measuring of distance is what UWB does.
Okay.
But not only that, because it has this detailed view with short pulses. It has a detailed view of the reflections that are happening. It can distinguish between cases when there is an aisle between these two people versus there's a person who walks between the two people. That, with the distance measurements being this accurate, was not possible with Bluetooth or with Wi-Fi control.
Got it.
That's why UWB played a very crucial role.
Got it. And this graph itself is some product of triangulation and interpolation.
This graph does not. Okay, so this is a ranging scheme, measuring distances only without doing any triangulation at all.
Got it.
This is like the lowest possible means of just distance measurement. And this graph is not a triangulation, but when you send a pulse, it goes and directly reaches the destination, which is this first peak. If you look at just the gray line over here, is the first peak that happened over here. That's the direct pulse reaching the destination. But then it also reflects from other places and it comes back repeatedly. And those are these reflections that you can see, which get manipulated based on whether there's.
What is the y-axis? Is it the?
It's an amplitude of received signal.
Okay, got it.
Yeah.
So any attenuation means something was in between.
In between, yeah.
Nice.
So there is the reason the y-axis is not well defined is because amplitudes are arbitrary. So it would be hard. It's only a comparison, right? Whereas no absolute numbers would make any sense.
Thank you.
Sure. Okay. So now we have a certain tool that can measure distance as well. Okay. And still during COVID, the other problem that we are facing, and even I'm facing with my son and so on, is online education, right? And I'm facing the same problem here while teaching. we are recording videos while teaching on the board, and that data has to be streamed to every student who wants to look at the video. And that's also how Khan Academy works, Udacity works, and so on and so forth, right? Lots of these online tools work exactly this way. There is an instructor who is writing on the board. We are streaming that data out. We said, could we, instead of this doing this huge data transmission, actually try and figure out where all this pen went or the chalk went, only record those locations, nothing more. Okay? And transmit just that much without modifying the tip of the chalk, right, or the marker, and without modifying the surface. Because you might say, hey, why don't you buy a $4,000 smart surface and then write on it with a $1,000 pen, and great, you get everything, right? Sure, the problem is that $4,000 smart screen, which now has to be installed in every elementary school's every classroom, right? So the barrier there is really huge. So we said, okay, we can actually do this. We want to, inculcate this idea of tiny data in education. And here is what we came up with. We have these UWB antennas in the corners of a large whiteboard. And this setup is a little bit more complicated, but I won't go into the details. And then there is a small setup. I have something here. Okay, this is not exactly what we use, but something similar. This is the form factor. So this was what we started off with. This is the form factor we started off with, and then we reduced it to about this big. Something that you can put on the back of a pen. Okay, so can I use the pen? So you have a pen, you're putting something like a cap on the back of the pen, and now you're writing on the whiteboard. Okay, you're measuring the distance of this back of the pen with respect to the three corners of the whiteboard. But there's a problem. Some people like write like this. Some people write like this. Okay? And you don't know where the tip is. Just measuring the back is not enough, right? Which is what we get distances from, but we really need the tip. And for that, we use an inertial sensor, which tells us the orientation of the pen. And then the length of the pen is, of course, known. And then you start writing and everything works. There's only one problem remaining. Did you touch the board, or were half a mm away from the board? Distance measurements can't give you that, because that level of precision is just impossible. From 2 meter by 2 meter board to take a look at half a mm change, which is really the difference between touching or not touching the board, was impossible. But then what we observed is, and also we couldn't modify the tip, right? We started with the premise that we can't modify the tip. We want to use the same pen. But then what we have observed is, whenever somebody starts writing, whenever the pen makes contact with the board, because it has friction, you have to hold the pen more strongly, right? Your grip has to have more force in the grip. So we actually put a pressure sensor on the side of the pen, not in the front, but side of the pen. And so as you start writing, the grip actually increases, and immediately we get a spike. That's where we know we have to start tracking. Right, and by not collecting any video, just by looking at traces, and of course, lots of algorithmic contributions here, architectural contributions as well. This is a multi-antenna system and so on. With the IMU and the force sensor all together, we now can do this. This is real time actually being plotted directly on the computer. We were still restricted doing all these experiments in the student's home, right, in a limited space, and therefore the whiteboard is actually very small, sitting on the directly on the floor. Yeah, sorry, I just wanted to go slide. And here is where we are from a data perspective. For 1 hour of writing on the board continuously, we require a total of 1.03 MBs of data. This is not Mbps. This is the total amount of data storage we need. Compare that with a 480p clip, which takes 213 MBs of data, and the 720 clip, we are not even reached 1080, which takes 400 MBs of data. Now imagine what it would do for Khan Academy videos to all be compressed 400x, right? And be all present on a pen drive. The whole knowledge of Khan Academy literally can be put into a few GBs of and write data. Not only that, in December of 2023, in a course project, my students demonstrated that it's actually possible to send that data over FM radio. This is all within a room, so not really far away, but over FM radio, and you get this. This is the transmitter. You wrote a hi on this transmitter, and that hi appeared on the other side of the screen. So now, using FM radio, there could be an instructor who is speaking, the teacher who is speaking, and the movements of the pen are also being sent on the same channel at the same time as the audio is going out. And on a student screen, it would render whatever the teacher is drawing. Literally free of the internet boundaries. You could now span 50, 60 kilometers using just one FM radio transmitter. And you could literally teach 10 classes at the same time, concurrently, because you can have 10 FM channels, right? And you literally run this for and think about wildfires, for example, that devastated large areas, and people have to go and live there to actually reconstruct. What happens to their children's education, right? What happens when you look at large-scale flooding events and so on? So this problem of education, not being able to educate because the school got flooded, is actually a real one, and even in the United States, right? And solutions like these can literally be deployed in a few hours and start to become functional. Not only that, the FM radio chip is actually present on all of our mobile phones. Just that. Very recently, most Samsung mobile phones have disabled that. Qualcomm chip still has it. Okay, we need to revive it for things like these to remain, because if we give it more years that it is never used, it will go away. The chip will go away. But these kind of utilities have not been explored yet, and there's a lot to do. It just makes access really different there. Okay. Thoughts, questions? Okay, go to the next topic. Thank you so much. Yeah.
One.
Go ahead.
Ashutosh. So at what point of the technology development or product demo phase is this work, or is it primarily theoretical?
No. This was demonstrated at the end of my last class. So December, mid-December, and this exists in the lab. And the students have set it up for me to demonstrate to anybody. This is short distance though. To do it long distance, I intend to talk with the radio team over here at Georgia Tech, because we do have a radio tower and really high capacity radio tower. And it should be possible to demonstrate it.
So if you successfully demonstrated, do you have some next steps planned, or where do you think it would be the most logical next step to this?
Correct. Some small hindrances that we professors face is the students graduate. So after doing the demo, but that's no hindrance really. So after March, I am aware that we have the bandwidth to actually try this out on a larger scale. But until March, the student is busy with another project, and that's the reason it is paused for now.
Yeah, no, but I was, you were talking about flood zones, and so I was thinking this is something that has possibly global development potential.
That's correct.
But I guess it's a little early stage. So maybe Kartik, can you frame my question better?
Yes, I will frame it. Why is this not a Sustainx company, Ashutosh?
It could be. It very easily could be. It is at a stage where we can demonstrate it. It is already, you can do a lot with what exists.
Okay.
The only thing that we have not proved is that it can work long distance, and what is the data carrying capacity when you have a little bit of loss and so on over FM radio transmission. That is the only missing piece really. So from a technology readiness level, it could easily reach the 8-9 level if a couple of months of dedicated grad student time could take it to that.
Got it.
Yeah. Yes. So, but the development only is a slight pause in some sense. Once the student is free from what he's doing right now, he would revisit this project.
Right.
Right? Maybe it's a good, potential demonstration for such an exhibition. So, and maybe there we could get more students who would be excited and actually try and take the next step.
Right.
This also ties in actually to the next work, which is trying to do this, trying to understand. Sure. Thanks so much. Trying to understand if we can perform gestures, record gestures, and interpret gestures just by looking at distance measurements between different parts of the body. And most people have not thought of this problem, but there are more than 600,000 people who use body signals on an everyday basis, and this spans more than 10 occupations, one of which being construction industry, but also aircraft marshalling, a lot of crane signals and so on, umpire signals, and the Navy to some extent. The usual idea is to perform this kind of setup. You have a camera that looks at a person, it captures the image, tries to do image processing, runs a classifier, and then says, oh, this was the action that was actually done. The problem, however, happens when the camera cannot see this person from all angles, and it gets occluded. Of course, the amount of data processed and data collected is significantly larger. You then, if suppose you want to capture a sports field, you need a group of cameras on the field. You need multiple such classifiers that do the deciding, and finally would give you an output of what exactly the umpire is saying. The problems are when you have a camera denied scenario, it's very dark, it's extremely bright, things like that, then you cannot deploy cameras. They won't work well. You have huge deployment costs, particularly for very fast moving things. The cameras have to be high quality as well. Huge amount of memory usage, architectural complexity, and processing. So our goal was to perform this accurate interpretation of signals, perform it in real time, be efficient in data, because otherwise cameras, for example, 99% of the pixels are basically irrelevant, and use just small number of sensors. And we have actually created 6 this size sensors, which 2 of which are worn on the wrist, 1 on the head, 1 on somewhere on the torso, and 2 on the ankles. This I should have just shown you this picture. Of course, sometimes fingers are also important. And so we have small sensors at the fingers. These are just photo detectors. So you know whether this finger was closed because there is shadow versus it was open because there is light. So putting all of this together, we are then able to stream that data from these 6 sensors, including inertial, so including the orientation data. So you can distinguish between hand being like this versus like this, right? Flipped around, as well as distances themselves. All of this data is collected, streamed to a computer, and then the computer actually does the final data processing on rather frugal amount of data, detecting the distances, the orientation, and finally giving you an interpretation of what that action was. Finger state detection is using the optical sensors as well. And here is what we have. So for example, this is the null signal. So when he was doing that, it was the dead ball signal. It started with a null, basically saying, I don't know what the signal is. Now this is a no ball signal. So in a few seconds, it says no ball. And he will, I think, give the wide signal after that. No, it's an out signal. And once it has interpreted, it would say out. So these are a few umpire signals in cricket, which uses essentially the same idea of using really small amount of data to produce final inferences. Let me go over the next few in a bunch, so that you can open it up for questions. What are we talking about here, right? We are talking about wireless signals that go and reflect from walls and different objects in the room and so on. If there is nothing moving in a house, the pattern that we see must remain stable. But if there is somebody moving in the house, like this person who started walking, we start to see these reflection patterns change. Okay, and this is something that your Wi-Fi access point observes, any wireless device observes as well, not just UWB, but with UWB, it becomes just easier to detect such changes. By looking at these changes, you can now install an intrusion, a physical intrusion monitoring device inside the house, which literally sits somewhere in the middle, does not have to be attached to every window, every door, but can monitor a large space. If there is anything changing in that space, it will immediately detect that and can raise an alarm. For doing all of that, we do not need cameras and we do not need IR sensors, which means a system like this can work across walls and can work for a much larger space, creating much fewer number of IoT devices needed to do the same level of intrusion tracking and detection. Also, because the sensor can sit in the center of the house, it's actually very difficult to disable it without setting it out. Right? And a student had actually created a nice demo for that. There's this lunch box that somebody wants to steal. Hopefully there is something nice here. And there are these UWB sensors set up. And okay, I don't know that the audio will be. How do I show that? Anyways, you see the student trying to walk, and whenever he tries to go near, it starts to beep. Now I can't turn on the audio because it will echo, but he's not able to reach there because it starts to beep immediately on these devices. He's trying from different angles. This, of course, is beeping. There is a light here which actually says that it's beeping. Anyways, but the point is, it is impossible to actually try and pick up without the signals detecting that somebody is trying to move. And then, of course, we can use similar kind of technology to track not just people, but also or intrusion, but also pets. And this becomes more interesting when you put these two technologies together, because now you can allow a pet to freely move in the house without triggering the alarm, while still triggering the alarm if somebody else starts to move in the house. Because the pet's device can indicate to the rest of the system that it really is me moving and nobody else, and therefore can be ignored. And any other disturbances are still caught, and then it raises an alarm. This, by the way, was showcased by Georgia Tech's communications team, which is the pet tracking project. And then finally, we created a reflections-based, just UWB reflections-based art system, which was actually showcased at Georgia Tech library for about 3 months or so last fall. And the idea is there's a large TV that you can see on the left-hand side, and you start to walk in front of it or start to perform some actions or dance, and the art changes. It becomes more vibrant when there is more action in front of it without using any cameras. It just uses wireless signals, and as the reflection pattern changes, it can look at that reflection pattern and create this kind of graphics. Right? So I have covered an array of topics that might seem disconnected, but they're all connected by 2 themes, actually. One theme is use wireless signals to do things that you otherwise do with cameras. And the second theme being the amount of data produced in doing any of this is minuscule compared to what cameras would have used to the same action. Your previous question, when you collect data to then later be able to do something that you didn't know you would want to do, remains a problem. A system like this can only function for when you know what you really want to do with that data, and then you design it properly in that particular manner. An open system where I'll collect all the data and then a next generation, can come up with some intuitive, interesting ways to look at that data. Very hard to support with such frugal amount of data in the first place. That's the alluring factor of cameras. That's where we are in some sense. I wanted to make one more connection before I stop, which is if you think about this project and then combine that with the writing on the whiteboard project, now it is possible to actually transmit the movements of the instructor along with the movements of the pen to actually create a system where you have a cartoon teacher teaching you on a whiteboard. Both the pen movement is correct and the teacher's movement is correct as well. And Beryl, it would be nice to have both of these systems actually implemented and put onto FM radio system, where then the experience will be very similar to what exists today. Because without that, we will only be able to show the movements of the pen on the whiteboard, but not really the teacher's movements. So the teacher's hands and so on. Right. But yes, with that, I'll open it up for questions. Thoughts?
Thank you. Yeah,
Thank you so much.
any questions in the room or online as well?
May I have one question?
Please.
Sure.
I think it's an interesting idea to look at tiny data proposition, which is low energy, low cost, and to look at a data environment that can be localized, decentralized, small scale. I've been thinking that it's a very different effort from current development of digitalization of our environment. For example, in architecture city planning, we talk about building information model, digitize the entire process from design, construction to operation of a building, and scale it up to a city or a much bigger environment in which you need a lot of data, expensive, and also from design to maintenance of such a system, we call it digital twin, right? Almost impossible. But this low cost, low energy environment might be possible to apply to some situation. There was a conversation session about global south, right? That kind of education. And what about for the situation when we have a disaster or post-disaster society that you don't have Wi-Fi, you don't have a large energy supply, but you can apply them to the small community that maintain the life support system and function using this kind of system. Just a remark.
Absolutely. Yes, absolutely. And not only that, when mobile phones have UWB-like technology, localization technology, in a disaster scenario, people could actually just enable that, or just mobile phones could be made to enable it just through broadcast systems. And then you would be able to dig out people from debris because their mobile phones can tell where they are. Right, that's an aspect that is already used in some cases in earthquakes and so on, but you cannot get accurately exactly where a person is. So that's one. The second aspect to it is liveness. If suppose there was a way to actually communicate liveness of the person to the mobile device, then we're not just digging out mobile devices, but actual people who have some possibility of survival after being developed. So that allows triaging and prioritization. And this is extreme, but it needs to be done in scenarios where there is earthquakes and a lot of debris around. So indeed, very useful in any system when you have a breakage of the usual infrastructure. Okay. Thanks so much.
Are you vulnerable to interference from, let's say you're at a cricket match and there's 100,000 people in the audience with also UWB broadcasting something. Does that present a problem?
So any wireless technology is always susceptible to interference. Wi-Fi, Bluetooth. However, every wireless technology has come up with techniques to avoid this interference or work with the interference. And in UWB, that's an underexplored space, simply because not so many people have UWB and they're not interfering with each other right now. However, it's actively being investigated by the UWB Alliance, and there are some very interesting opportunities in UWB. Because it's a technology that can measure distances very accurately, it can also tone down the transmit power based on the measured distance of the peer that we care about. Right? So what you can do is on a cricket field, for example, the umpire system just is a body system which should work on body. Right? So somebody in the stadium should not interfere with this person at all. And therefore, they should be able to reduce their power as well as the person in the stadium should be able to reduce their transmit power so that this interference will not happen. Now, in general, is jamming attack possible? Absolutely, yes. It's an open ISM band, and on ISM band, anybody can jam, except that there are other provisions to try and catch these people who jam. Right? But yes, jamming can occur in UWB. So if you need extremely reliable transmission, right? Then you wouldn't use UWB. However, what we have also shown in a recent paper, not in this talk, but we have shown that localization can also be unspoofable. Means people cannot lie about their location. So long as you have support from a few other devices who are overhearing the signals, it's actually not possible for a client device to lie about its location. Because if you think about localization as a deployment, right? We're talking about a factory where every worker's tag has UWB, and that gives them access to their card. Basically, their access card has UWB and gives them access to all doors and various areas. But it also allows people to track where they are so that they're not stealing from someplace and so on. Now there is an incentive for this person to actually spoof their location and say that I was there versus when they were actually here. It creates issues. So very recently we have come up with techniques which stops such spoofing from occurring. So this does not solve the interference problem, but it at least solves the cheating problem of lying about where you are.
Can it also create a network?
Yes.
So, I mean, you transmit something
Yes.
low to me, then I transmit to
Yeah.
her, she transmits to him,
Correct. Yes, it can.
and we don't need a cell network.
You don't need a cell
anymore.
Ad hoc networks are possible using it. You had a question?
Correlated to his question, could you provide some historical context to why ultra-wideband is an opportunity now versus the 90s?
Oh,
There's
sure.
a lot of interest.
That's a very good question. So actually the answer is deep within this slide. Why am I not powered up? When you have very large bandwidths, like these 500 gigahertz band, 500 megahertz bandwidth over here, my mouse won't move, but you see here, you need an analog to digital converter, which can sample at that fast rates, right? And that needs a lot of technological advancements to be able to do that in these small form factors. That was problem number one. It took us a few years to actually build the electronic circuits, oscillators, and so on to the scale that would be needed for IoT devices to have ultra-wideband radios. So if you look at papers from the 2000s, when UWB was also popular, those papers had actual oscilloscopes with these big machines, which are capturing these data, and there are signal generators that are generating the data. You would see similar graphs, but those devices are impractical. You can't carry them in a pocket, right? That was problem number one. Problem number two is a very interesting one, because in computer science, we try to solve problems like these, not in ECE, I'm in computer science. So we try to solve problems of algorithmic implications. And the ranging protocol, the protocol that tells us the distance between an object from another object, requires you to take care of two problems. One is clock offset, and another one is clock drift. Okay, clock offset means my phone shows slightly different time than Mike's phone. Okay, and that time is say 1 minute apart, and it keeps remaining 1 minute apart forever. That's clock offset. But clock drift means all of our phones are not able to exactly tick at the same second, and therefore over time they show slightly different varying behavior. Okay, that's clock drift. And when we're talking about nanosecond level accuracy, we're talking about clock drifts that have to be minuscule, that have to be extremely small. It's very difficult to build clocks that good. Okay, so we need algorithmic solutions to cancel out these clock drifts and clock offset errors. The original algorithmic solution to do that had a problem. It required both devices to be equally capable. Only then it worked well. But then in 2016, the company Decawave, which actually features here as Corvo, this Corvo is the company who bought Decawave, they came up with an algorithm which allowed, actually not even an algorithm, just a formulation that allowed to mitigate the clock drift error. Okay, and once they did that, it opened up this localization space. In fact, IEEE revised their standards to incorporate this new formulation, creating the 802.15.4Z standard, which now 2020, which now uses this new formulation from 2016. At that point, it opened up so many new applications. Almost my entire set of UWB work would not have been possible if DECA didn't have come up with that formulation. Okay, and eventually we solved the problem for time difference of arrival and so on, similar manner, and now it is possible to just have a mobile phone which never transmits any data, it never gives away any of its private information, and still localizes itself, just like GPS does. Okay? So that's why work is still in progress on the UWB space. And just now, Apple has come up with products which allow you ranging. Still not localization, it's just ranging, distance between my objects that are lying around the house. Okay? But yeah, very exciting space for sure. And touches so many different domains. That's why it's exciting.
Thank you so much.
Thank you.
Wonderful.
Thank you so much for hosting me.
Discussion, yeah.
Thank you.
All right, nice.
Thank you all.